Hi, we present open source iris recognition hardware and software with presentation attack detection. This is a work done by Zhao Yuanfang and Adam Chaika from the Computer Vision Research Lab at the University of Notre Dame. Our motivation for this work is that we observe that very few works have been published along the lines of open source iris recognition, and all of them lie in a software domain only. None of them touches the hardware domain. Therefore, our goals for this work is that first, we want to propose an open source baseline to stimulate iris PAD research and allow for easy prototyping of secure iris recognition systems in the sense of both hardware and software. Second, we want to offer a low-cost, secure iris recognition alternative to more sophisticated systems that are currently in commercial use. And this may serve as an educational platform for iris biometrics. Our hardware design is based on a Raspberry Pi, and it is low cost and easy to be assembled. From the table on the right, we can see that the total cost of this entire system is less than $75, and that takes into account all the possible elements that we're going to use. So our hardware design includes first an infrared sensitive camera that captures iris images. Then the illumination is controlled by a circuit connected to the Raspberry Pi. We are taking two illuminations, so the two LEDs as you can see in the image on the left. And then the Raspberry Pi performs iris segmentation, recognition, and presentation attack detection after the acquisition of those two iris images. An example image captured by our Raspberry Pi overlaid with our segmentation result is shown in the middle here. Here we're going to talk about our software design, which includes iris segmentation, recognition, and presentation attack detection. First, we're going to talk about segmentation. Our segmentation network is based on a retrained CCNet model, which is a lightweight and image complexity-based compressed segmentation neural network that has a similar architecture to a UNet, but much less parameter. Our model runs 3.5 times faster than the popular OSIris open source iris segmentation package and 37 times faster than the state-of-the-art deep learning segmenter, SegNet. And therefore, this makes our network ideal for the deployment on a mobile device with limited computing power, such as Raspberry Pi. And from the table here, we can see that we have much less trainable parameters. Although OSIris does not have any trainable parameters, the Viterbi algorithm underlying there takes a lot of computation power of the CPUs. From the iris segmentation images, we can see that our method segments the iris very closely to the ground truth. And both another model, another UNet used by another group, and the open source iris and SegNet sometimes doesn't generalize as well to the Raspberry Pi segmented captured images. Our software design part 2 is iris recognition. For this part, we adopt the state-of-the-art iris recognition algorithm based on domain-specific human-inspired BSIF features. In this approach, our filtering kernels are learned from regions that appear most important to human performing iris recognition task. We include image patches that correspond to correct matches made by the human from both their eye gaze and their regions of manual selection. For our PAD component, we adopt an ensemble classifier to combine both the 2D textural features and 3D photometric stereo features to make sure that our PAD is robust. and it is able to detect unknown contact lenses. The idea of our 2D classifier is a BSIF histogram-based ensemble classifier, and our 3D features are derived from the observation shown on the image on the left here. So when an iris is illuminated from different directions, the shadows in it will be different, and this difference is most well pronounced when a contact lens is worn by the eye. And on the right here, we can see the joint score distribution of our 2D PAD and 3D PAD. A very simple fusion rule arises from here, and from our experiments, it is robust to many cases. So we can take the samples that classified as contact lenses by the 2D, and then for the rest of the samples, we can just use a 3D classification as our final result. The performance of our system is both fast and accurate. It is fast because our implementation takes advantage of all 4 cores of the Raspberry Pi through multiprocessing, and we make sure that we achieve the fastest speed possible on this mobile platform. And here on the image on the left, we show a motivation of why PAD is crucial for iris recognition systems. We show that when the genuine irises are covered by textured contact lenses, the score distribution shifts towards the imposter distribution. Therefore, PAD is very important before doing the matching. On the tables here, we see that our method performs with high accuracy, separating the genuine and imposter groups very well. The processing times are also tested on the NDCLD15 and NDIRIS 3D datasets. We see that the entire system is very efficient, given that it is run on such a small Raspberry Pi. And that's our presentation. If you have interest in more details, please check out our paper and the codes and assembling instructions available on GitHub. If you have any questions, please feel free to email us. Thank you so much.